Okay, a while ago, right, we talked about correlation and spectral density. 2 minutes, right? 2 minutes long. So, last lecture before the midterm exam, we talked about noise and signal to noise ratio. So today we are going to start talk about correlation. Correlation actually talk about the similarity of signals, right? Two signals. How close two signals each other. Okay. Yeah, at first we gave a definition for correlation. So correlation function defined here in this textbook as something similar to our correlation convolution. Okay, RF tau is correlation. If we have power signals, we have signal conjugate mix or time signal with a sheaf. Then this tau actually is going to change. We calculate the integral normalized by t. This is O2 correlation. Okay. Very soon we are going to show examples. How can we find given signals correlation? And remember lecture 1, we talked about how can we find power signals, power spectral density, right? We talked about 4.17, right? 4.20, two methods. Today we have the third one. This one is more popular than the previous two methods. If you know RF tau, autocorrelation signals, Fourier transform is power spectral density.
Is that the conjugate of it?
Yes, conjugate. Yeah, the star means conjugate. Okay, so here is the equation. Then we are going to show example. Okay, this example is from your textbook 4.4.1. We are going to find the autocorrelation function for a square wave. For square wave. So we have a square wave, right? This signal is square wave. Is capital T, right? Capital T with peak-to-peak amplitude A. Oh. Okay. Peak-to-peak amplitude is A. Mean value is A half. So this is the signal we have. We want to find O2 correlation. So let's go through it together. Because my signal is periodical, so we are going to find the autocorrelation over one period. So we can. Okay, so we just evaluate the correlation in one period. Because my signal is real signal, so real signals conjugate the same, right? The same. So now the following procedure will be very close to the one we showed for calculating convolution of two rectangular signals. Okay, so I'm going to explain what's going on here. So the first term, we have ft, right, fixed. The other one, we have time shift, right, time shift. Any problem? So let me. Plus t over 4. This is my ft. Plus tau. So depending on your tau is positive or negative, I'm going to shift either to left or to right, or to right. So when tau less than 0. So when tau less than 0. Oh, in our textbook, it also did some change for this problem. So okay, in this one. So let me do this, otherwise you cannot follow. So S. Okay, in our textbook, it did this kind of variable change. Variable change. So we have f t minus tau ft dt. So here we have f t minus tau. This one will be exactly the shift that we showed in the example. Okay, any problem? How can I get this one? Here I just do the variable change, right? Variable change, and here I take this conjugate off because this is a real signal. So this is my ft. This is ft minus tau. Then tau less than 0. Just a minute. Just a minute. So when tau less than 0, I minus a positive. I minus a negative value, I'm going to shift to left, right? Shift to left. So here is tau. Here is tau. So I shift it to left, and we calculate the overlap, right? Multiplication between ft and ft minus tau. So this is the overlap, that overlap. So my boundary from minus t over 4 to t over 4 plus tau, Okay. So minus t over 4 is this one, right? This one is plus tau. So this is our textbook gets the solution. Okay.
I don't think that. So we went from the conjugate of f of t to the conjugate of f of t minus tau. And that's equivalent to f of t minus tau
Yeah.
f of t.
Yeah.
So the conjugate didn't serve a purpose there?
Because my signal is real signal.
Okay.
Yeah, because my signal is real. But for complex signal will be different, right?
But isn't it supposed to be complex?
This is complex?
No, not necessarily.
Yeah, know this one, right? Know this one. But if you have dj omega t, this one's conjugate will be e minus j omega t, right? But for this one is real. This one is real.
did you get the f of t minus tau instead of f of t plus tau?
You can, for example, use v t minus tau plus tau, right? Plus tau. Right. So if I let v equal to t minus tau, I'm going to have here f conjugate v minus tau, right? F v. Then change v to to t again. So if I'm doing this, I'm not going to do this. I'm just going to ft plus tau and do the shift. But our textbook did this, so I just want to follow their procedure. So if you take a look at your textbook, it mentioned this one is equivalent to this one. Yeah. Yeah. So generally will be the same, right? No matter plus tau or minus tau, will be the same. But however, if just to avoid the confusion, right, then you look at your textbook or the textbook. Okay, so the main thing is, right, when I shift it, my overlap is changing because of tau. When tau less than zero, I have overlap like this. So I do the integral. I get one side, right, one side. The other side, when t is positive, I shift to right. So here's my when I'm going to shift to right. And in this case, my overlap will be the new shaded area in red color. So this is next slide. So from tau minus t over 4 to t over 4. So this is exactly in our textbook. I give you a little more details, so it's easier for you to follow. So very close to the one we calculated convolution, right? Shifted different overlap. So we discuss for different tau value. And the final answer, autocorrelation for square wave is triangle wave, right? It's triangle wave. So we have increase, so you can imagine as the overlap is become bigger and bigger, then becomes smaller and smaller. So it becomes bigger and bigger, then smaller. So you can imagine, right? You get a triangle wave. Any problem for this one? Okay. Now we are going to move to the next example. Next example will be much simpler. Okay, so example 4.4.2, we want to calculate autocorrelation function of sinusoid. Okay, so over here, okay, so for find the autocorrelation function of square root of 2 cosine omega 0t plus theta. We are going to use the definition, right? The definition for it's this And my signal is also periodical. We also just consider in one period. One period. Okay. So this is ft conjugate, because my signal is one more time is real. So cosine conjugate will be the same cosine. So this is ft. This is ft plus tau. T plus tau. And integral normalized. Okay. How can I get this one? Cosine time cosine, we get cosine plus cosine, right? This is one equation in your appendix. So cosine. Okay, so we have the difference, right? Difference and the summation. Okay, I can say this part integration is 0. Any problem, how can I get this one? So we did this for many times, right? I have sinusoid over periods. You can view omega 0 tau 2 theta as just initial phase. We get 0. Okay, for this one's integral, we get cosine omega 0 tau. We can view cosine omega 0 tau as a constant, right? Move it to outside. Let me write down just this spectral. So I get cosine omega 0 tau. So my correlation is only related with time difference. We can also find when we do the correlation operation, initial phase theta is gone. There is no information about theta anymore. But we get the frequency. Right? Frequency is kind of extract from the operation.
How come the root 2 went to a 2 from the initial function?
Yeah, root 2. So I have f conjugate times f, right?
Oh, gotcha.
Yeah. Yeah, I have f. Right. Okay. So autocorrelation tells us a signal with itself relation, right, when there is a time shift. For example, rectangular signals correlation is triangle, right? Sinusoid signal correlation is also sinusoid. Any problem with this? Okay, so now I'm going to talk about how, right? How can we use correlation in real applications? I'm going to show one example. This one is also from the textbook. So I have a square wave. Square wave oscillation is triangle. We know that. And if we consider the first signal is a message, right? I transmit 1001, and most likely my signal will be interrupted by noise. So this is the noise. And this noise is pretty powerful, right? So when my signal plus noise, this is the received at my receiver. I cannot tell what is this, right? Just like noise to me. However, if we calculate the correlation, this is correlation of the original one. This is the correlation of the noise. Noise is random. So most likely noise has no similarity with itself. And this is the received signal's correlation. So we can tell, right, the transmitted signal is very close to a square wave. So we use correlation in real life. For this one, okay. Now, instead of auto correlation, we talk about cross correlation. This one is much more popular and widely used in different areas. Cross correlation, so we have two signals, right? We have F and G. FT is one signal. Okay, conjugate. If it's real, will be the same. The second term in your equation will be signal number 2. So GT with a shift. So we can tell how similar one signal with another. We call this one cross correlation. Cross correlation. For this one, the calculation, right, will be similar. And I would like to talk about how are we going to use cross correlation in communication, also in signal processing. So very easy equation, right? But after we're done, we'll talk about the examples. Okay, this example is we use communication as a example. Right, my signal goes in, received here, right? Received here. So that's one important thing we have to do. We call it synchronization, right? So you want to synchronize, right, the two signals. You want to know what is the starting point, right? What is the ending point. So we use cross correlation to find the delay to synchronize two signals. This is the most popular method we synchronize two signals. So for example, this is FT, right? Signal I transmit, and it will arrive at my receiver with some delay and also mix with noise. So when it's received over here at my receiver, it changes to something different, right? So we'll have the random signal transmitted plus a noise, then with a shift, with a delay. So this delay may be introduced by the transmitting time, right? Modulation, demodulation. So many things, right, can introduce delay. So this is the signal I receive. I want to synchronize two signals. What can we do? We use correlation. So this is the cross correlation between the transmitted one and the received one. You can imagine, right? Those two signals close enough or have the highest similarity when there is no delay, right? When they're just synchronized together. So the highest correlation happen at I have no delay. So here, this tau gives me how long is the delay. We use cross correlation to synchronize signals in communication systems. Okay, any problem, any questions for this one? So it uses a lot. GPS, right, you synchronize with different satellites, use correlation. more examples. But before something fun, we go to something interesting, right? Not boring, interesting. For correlation, we also talk about properties like convolution. Okay, not boring, very interesting. Later we have more interesting stuff to talk about. So correlation function, like we mentioned, triangle right over there is symmetric, and conjugate symmetric. So RF minus tau is R equal RF conjugate tau. If it's real, conjugate is gone. So your correlation function always be symmetric. Okay, this one is very important. Now, mean square value we know is also power, right? It's also power. So we have the force, right? Number 4 method to calculate signal's power. So signal power or mean square value of your signal equal to RF0. So 0 of your autocorrelation function. Very easy to figure out, right? When there's no time shift, right? Ft conjugate times Ft, we get power, right? We get Ft. So power. If you know correlation, you can just find your power by take a look. Okay, periodical. If your signal is periodical, correlation function is also periodical. So we can just only evaluate, right, the signal correlation in one period. And they share the same period, capital T. So the example we just showed, right? Square wave period is T, right? The triangle wave also T. And next one, if we know two signals cross correlation, RFG tau bar, the mean value of your cross correlation is M1 times M2. M1 is signal F average. M2 is signal G's mean value or average. Okay. I have one more, then we talk about something interesting. Oh, yeah. Two more. Okay, this one is easy to understand, right? So maximum value is RF0. When there is no time shift, you have the maximum, right? Similarity. When there is a shift, your similarity will decrease. Additive. If I have two signals add with each other, the combined signals autocorrelation related with autocorrelation of two individual ones and cross correlation xy and x. Okay, most of the time they are the same, right? But sometimes they may not the same. So we still write rxy and ryx, but most of the time those two are same. Okay, so 6 properties, and later we use properties to do some problem. Okay, any problem so far? Now I'm going to talk about how can I use correlation in real application. I'm going to show one example in biomedical signal processing. Okay, so we use cross correlation in biomedical signal processing. So you heard about MRI, right? MRI, magnetic resonant imaging. So we can figure out what's going on instead of cut human body. And did you hear about fMRI, function MRI? Maybe not so popular, right? So MRI give our static image. Function MRI, we find we get, okay. So this one measure the signal change, right, in your brain. So most likely function MRI will in your brain. In other organs, right, there's no so much change, right, for the electronic signals there. So function MRI, we measure the signal change in your brain, So those signal change due to the changing of neural activities. So we are going to still do the same thing. We are going to scan human being's brain at lower resolution, but faster speed, so we can see, right, the change. So it's very useful for those, I don't know actually, very useful for some measurements, right? Yeah. So diagnose, right? So physician, no, I don't know, but they give me the images, right, to process. So increases in neural activities, the signal we observed by those images also changed, right? More active, right? Changing faster. So very easy to understand. So we are going to find how are we going to use correlation here in this application? There are many tools, right, to help us observe and analyze the MRI images. So we know for those commercial use, right, medical use, really expensive, right? $1 billion of equipment, right, plus software. And for researchers, right, like us and the students, there is one called AFNI. So that one is based on Linux system. It's open source, so it's free, right? It's free. So we use AFNI to do our research, right? So in that one, correlation is a very important thing we can adjust. So what we do, we want to find connection between stimulus signals and the thing we measure. So we want to know. Let me show you. Okay. So when we do the MRI, we have images, right? Those are the active small portion. Each small portion we call it a voxel, so thing like pixel. We model it as a system. Yeah. So we model a small portion of your brain like a box, a black box, a voxel. So we model it as an LTI system. We have input. This input will be some stimulus function. For example, when you listen to music, music will be stimulus signal, the input to your brain. And which part is processing this signal will be audiology, right, or brains in charge of carrying, right, or perception. So if we ask patient tap the finger, or tap his finger or her finger, this signal will be considered as the input. Right? So which part in your brain is processes tapping finger activity? So we look at the whole entire image of the brain. So which one has the highest correlation with the tapping finger signal? That one will be the part, right, deal with this activity. So we know, okay, this part is charged tapping finger. If people look at picture, right, or watch video, you just find the correlation between many outputs, right, and one input. The one give you the highest correlation is